the thing I want to play you is a cannon. Remember we talked about cannons last week? This is my favourite cannon of all time. It's completely awesome. Oh, it's not this one. No, that was just some noise to check we've got sound. It's called Dan and Nad. But it's a cannon. Dan and Nad.
Oh, hi everyone. Dan and Dan here. We were having a bit of a birthday celebration, haven't we? Yes. Unfortunately, Dan's not feeling 100% now, are you? Maybe actually personally, you might understand how much it is, you have to have sentences and so on. You see, when he blew out the candles on his cake, he made a special birthday wish. Guess how much he does. Something about getting younger instead of older, isn't it? Not sure he was expecting it to come true quite in the way that it has, but you know, he has though, do you? So what he was just for the party trick, so that was very good. It was always nice, but they made me dig it in. Actually, I'm quite envious now, because in a few hours you're going to go to bed with a blinding hangover and then wake up, essentially, in the pub. Well, the nice hole has it. They're talking in the pub. You've been there for a couple of years, mate. You should lose about a stone in there. Anyway, I haven't made my wish yet, so I'm pretty sold on this. I think I'm going to join it. You ready? How's it for you now? Thank God for that. You know, you've always been like that. I said, well, let's see her come up. Yes, she'll be on the end of the house. Yeah. And the outside, you know, you're like her to have it. Well, I think good, but is that what I sounded like? Well, then you just mess it up. No, and then everything. You know, the back there, there's everything. I do that. Where's that? He may be getting younger, Dan, but he sounds like a drunk Jim. And it's over. Happy birthday, anyway. That's the only elf. You're relaxing, happy to emotional. I don't want to alarm you, Dan, but you're going to need to go to the toilet at some point. Well, that's annoying, yeah. Something which I can only imagine being slightly traumatic. I also suggest a birthday dinner somewhere nice tonight, but I'm not really sure I can take you anywhere now. Yeah, let's bring all these ones tonight. You see? What?
That's awesome, eh? Did that make sense? Yes, very good. Thanks, Don. Say that again?
Your computer doesn't have sound.
Oh, it should. It should. Maybe I'm just plugging into the wrong thing all the time, but hopefully now I've got it right. What's that? Yes. Oh, yeah, that's what I did. Yeah, I can always get them mixed up. Yeah. Dylan pointed out that I've been plugging there's two sockets on my computer, and I've been plugging the sound plug into the wrong socket. Who'd have thought? Now, I want to just quickly do the answer to the barometer puzzle. Just while those that don't want to hear it are hopefully out of the room. Do you remember the barometer puzzle? You've got two barometers, you've got a big building, you want to drop the barometers from various heights inside the building, different floors, maybe from floor 36 maybe from floor 52, and you want to precisely calculate what is the first floor that's so high that it will cause the barometers to break. And they're both identical, so they both break from the same thing. But once they're broken, they're in little pieces and you can't repeat the experiment. And remember, we looked at it, the really naive way would be to start from the bottom, just going up one floor at a time until they broke. But in the worst case, if the building was 100 high, you'd have to do 100 steps. And then we looked at, you could do divide and conquer. If you had log of n barometers, you could just do the halfway points and just narrow it down really quickly that way. But if we only have 2 barometers, we've got to do something in between the 2. So how do we solve it? And the reason I wanted to talk about this today, and the reason in fact we introduced the puzzle at all, was relates very much to exactly what we're looking at right now. This is how I solved it, and I got to apologise because it's probably quite a long and elaborate way compared to the standard way of solving it, and it may also not be the best solution. But the way I solved it was by using recurrences. What I did was I thought, oh, let's think, what could a strategy possibly be? I'm going to drop the first barometer out of one floor. I don't know, suppose I drop it out of 36. And there's 2 things that could happen. Either it breaks or it doesn't break. I've only got one barometer left. What do I have to do now? I have to start from the bottom and go up. So if it breaks, I know I've got to do 35 work. If it doesn't break, then I've got to follow some sort of strategy using 2, but now I've got a smaller range to search. So it looks like the original problem repeated, but a smaller instance of the original. Now, I was interested in the worst case, the one that does the most work. So when I was thinking about it, I thought, well, I guess the worst case is going to be that, to have a strategy which deals with the worst case, I guess I want to have it so that if I drop it and it breaks, I do exactly as much work as if I drop it and it doesn't break. So to be proof against the worst case, I want to make the worst case as small as possible. I don't want, if this happens, I do more work than if this happens, because then it will always pick this one. I want to shuffle work across. And I don't want to have it that if this happens, I do more work than this one, because then the other 3 will make this one happen, I do more work. So I want to balance the work between them. I want to move work from the hard case to the easy case, making the easy case harder and the hard case easier, so they're both the same size, and then no matter which way the adversary picks, I'm going to do the same amount of work. Yeah, so that was it. So then I thought, okay, so the amount of work is the number of comparisons I've got to do. So the number of comparisons I've got to do if I've got F floors, say, well, if I do my first dropping point at floor number K, then it's, if it breaks, I have to do K work, or else I have to do C of what? N minus K, F minus K. Yeah, I've got F floors to the building. I've done it at floor K and it didn't break, so I know it's somewhere on the top, so I've got F minus K floors left to look. So looking at that, and I was actually, when I was thinking about it as I was walking home, I only just discovered this puzzle recently, and I was walking home from a lecture here, and I remember exactly where I was standing when the realisation hit me, and I don't know what it is about that. The only things I can remember at life are important moments, and for me that was an important moment. I suddenly thought, oh, I know how to do this. And I was standing outside a garbage bin on one of the student accommodation blocks quite near here. So that could be your garbage bin that now has a special memory for me. That tells me that C of F minus K has to equal K. Because I want the same amount of work to happen. Oh, actually that's K minus 1. Equals K minus 1. So the smaller problem, I know exactly how much work it's going to involve if I want things to be balanced. If I work out a clever strategy for this half, that's my ideal strategy. It'll have this amount of work. Now, so looking at this, I guess at this point in time, I suddenly could see, because I could see this recurrence, I could start to see how this recurrence was going to work. then I'm going to be adding together a whole lot of numbers. I'm going to be adding together a k minus 1 and a k minus 2 and a k minus 3 and a k minus 4. I'm going to be adding up all the bottom halves, and they're going to be exactly equal to the sum of all the top halves of every options. And the top halves are hard to work out, but I can add up the bottom halves really easily. And so, I can also see that, yeah, okay, so it's k minus 1, and then next time it'll be k minus 2, then k minus 3, and k minus 4. Let's try an actual number and check it. If we've got 100 floors, and I did it at floor number 50, say, the cost is how many times I'm going to drop it. Oh, yes, yeah, so the cost is how many times I'm going to drop it, and I'm going to have to drop it k minus 1. Yeah, if this fails, I'm going to have to drop it 49 times.
But if it succeeds?
If it succeeds, I'm going to have to drop it 49 times too.
You have to add the cost of like actually having to check if it breaks.
Oh, sorry, yeah, thank you. Thank you. I drop 1 from my floor at level k, and then either, if it breaks, I do k minus 1 other comparisons, or if it doesn't break, I do CF minus k comparisons. Now, this time, I didn't have a pen and paper to work it out, but I could just in my head, unrolling this a few more steps, iterating this a few more times, I could see I was adding together a sequence of decreasing numbers. I was going to add together k minus 1, k minus 2, k minus 3. I thought, oh, okay, that's going to give me an n squared. And I thought, oh, okay, so the answer is going to be some sort of square rooty thing. And then I thought, oh, okay, so everything's sort of backwards. So at that point, I decided to reframe the problem, and I would work out the maximum number of floors I could solve for a given number of comparisons. Now I'm not going to have square roots, I'm going to have squares, and that's just so. So the maximum number of floors I can solve for a given number of comparisons. Let's have a look. We'll just start with the base case. If I've got just got 1 floor, it takes 1 drop. So for 1, it's going to be 1. If I've got, if I can do 2 drops, then I can handle actually 3 floors. Can't I? I do 1 at this floor. If it fails, I do 1 there. If it succeeds, I do 1 there. So for, if I'm doing 2 drops, I can get a 3. If I do 3 drops, then if I'm going to do 3 drops, let me get it right. I'm going to be able to drop it here first of all. If it fails, I'll do 2. Have I got it right?
Shouldn't it be 7? Because you can do 1 floor in the middle and then the same problem below it and above it.
If it fails, I've got to do two more comparisons. If it succeeds, I can only do 2 comparisons. And to do 2 comparisons, I can do 3 above it. That's the old one, plus 3. So it's the old one, 3, that's solving the old problem, plus 3. So that's 3 equals 6. 3 goes to 6. All right, if I can do 4 drops, bear with it, because eventually this will make sense. If I can do 4 drops, then I'll do my first drop has to be 4 up, because if it fails, I can do 3 below. Yep, I can solve that in 3 comparisons. How far up can I go in 3 comparisons? Because this gives me 2 to work around with, whereas here I've only got 1. Using 2 and 3 comparisons, I can do 6. Can you see? So the total number now would be 6 plus 4 is 10. Yeah. If it fails, I can do 4. If it breaks each time, if the first one breaks, I can, the remaining 3 drops, I can work out 3. If the first one doesn't break, then I've got 2 barometers, and in 2 barometers, and I've got 3 drops to do it, because my challenge is to do it in 4 drops, and I've already done 1. With 2 barometers and 3 drops, I can do 6, because that's what I worked out last time. And so for 5, what's this? You have failed the acceptance test Damn, should have used enums. All right, suppose we can do 5 drops. Well, if we pass, so we're going to do, if we do our first drop at position number 5, and if it breaks, then I have to work up from the bottom. I'm only allowed 5 drops, so I've used one of them up, so I've got 4 drops left, so I can do 4 working up from the bottom. But if it succeeds, if it doesn't break, then I've got 4 drops left and 2 barometers. How much can I do with 4 drops and 2 barometers? I can do 10. It's the old value, 10. So it's 10 plus 5. So can you see in every case, it's K plus the previous value that I've worked out. Does that make sense? So for 5, it's going to be the previous value, which was 10, plus 5, which is equal to 15. And for 6, it's going to be the previous value, which is 15, plus 6, which is 21. And for 7, it's going to be the previous value, which is 21, plus 7, which is going to be 28. What's this sequence here? 1, 3, 6, 10, 15, 21, 28.
Perfect numbers.
Not perfect numbers, though 6 is a perfect number and so is 1. Oh, in fact, so is 28. Is 28 a perfect number?
Yeah, but 21 is a
No. Triangular numbers. Yeah. These are the triangular numbers. What are the triangular numbers? They're 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, 1 plus 2 plus 3 plus 4 plus 5. The only thing you ever need to know, remember? We keep saying it. If you have to work it out afresh every time I show it to you, you're wasting your time. You should have learnt it once and memorized it. It's one of the few things in the course you should memorize. I expect you to know how to add up 1 plus 2 plus 3 plus 4 all the way to n. And I expect you to know that inside out. And whenever you see it, I expect you to see it because we've now seen it, I think, 8 times in the course in different contexts. And it will come up again. I guarantee it'll be in the exam. Okay. So absolutely, that's something worth memorizing rather than working out on the fly because you're just wasting time. And in an exam, you have no time. So what is this? What is the sequence that for n gives you the nth triangular number? So for 1, it gives you 1. For 2, it gives you 1 plus 2. For 3, it gives you 1 plus 2 plus 3. For 4, it gives you 1 plus 2 plus 3 plus 4. For n, what does it give you? If you have to think, punch yourself in the head, burn your hand under a hot tap, incorrectly working out which is hot and cold, because this is something you've got to know. It's got to be n times n minus 1 all over 2, or n times n plus 1 over 2. It's got to be order n squared. Yeah. Yeah, it's a minus 1 or a plus 1. Yeah, you have to. I can't ever work. Minus and plus I can never work out. You have to know it though. It's order n squared. So this is growing n squared. So that's your strategy. Does that make sense? Can you see the strategy now? The strategy on rolling backwards is if you're going to do it, the number of drops you're going to have to do, the number of floors you can do in a given drop is n squared. So if you've got a 100-story building, well, luckily that's a square number, you're going to be able to solve it in 10 drops. And your first drop is going to be at floor 10, and if it fails, you build up from the bottom. And your next drop will be 9 above that, and your next drop will be 8 above that, and your next drop will be 7 above that, and your next drop will be 6 above that. Yep, they're all your drop points if it's not breaking each time. And then as soon as it breaks, you just work up from your last known good point. Does that make sense? So you can derive the strategy, run the strategy backwards. Now, why is this an important thing to see now? A, because it had a recurrence relation in it, that somehow C of f was related to C of f minus 1. C of f was actually equal to C of f minus k plus 1. So C of f was related to a smaller instance of C of the number of comparisons, the number of drops you have to do for a given number of floors is related to the number of drops you have to do for a smaller number of floors. That's called a recurrence. We see recurrences all the time, and we're going to see, we saw like Fibonacci is defined with a recurrence, right? We're going to see recurrences a lot. Recurrences are really cool because when you get a recurrence, what it's telling you is you can solve the original problem by solving a smaller instance of the original problem. Now, in the remainder of today's lecture, we're going to be looking at something called dynamic programming, though we've actually been looking at it all day today. The previous lecture was on dynamic programming too. Dynamic programming, was invented by an awesome guy called Richard Bellman. he was under a regime when he invented it of the military being, and the government of America at the time, being very, very hostile to theory and mathematics. And he was employed by the Rand Corporation, and he was trying very hard not to look like he was doing any research or any mathematics. So when he wanted to fool around with ways of solving problems, when you've got a problem and the solution to it is somehow related to a solution to a slightly smaller instance of the same problem, and he wanted to work out the optimum way of solving it, the optimum way of scheduling. Here we were trying to schedule which floors should we drop it from. We were trying to come up with a table of, if you drop it from this floor and it breaks, what do you do next? If you drop it from this floor and it doesn't break, what do you do next? And we could write out a big flow chart and give it to some person who didn't understand the theory of what's going on, and they could follow it out. He wanted to work out, how can we work out this optimum strategy, this correct way of solving problems like this? He was very, and these problems appear all the time. We'll look at a whole lot of examples at the end of the lecture. But the problem was, if he said that's what he was doing, coming up with a mathematical analysis of ways of solving interesting problems that involve recurrences, that involve smaller versions of themselves, he would have got chucked out and everyone would have been crossed. So he thought, what I've got to do is give what I'm doing a name that doesn't give any clue at all that it's got maths or anything theoretical, and it's got to sound really practical. Now in those days, programming didn't mean what we call programming to be, because computers weren't that big. Programming then meant just scheduling. Yeah? How do I schedule my factory machine? How do I run a program for the exercise regime or something like that? It was just working out scheduling. And dynamic he picked because it sounded really neutral, and there's no way you could think dynamic was bad. So he said, I'm calling it dynamic programming. And now we use it in programming all the time, but it's a sheer coincidence. And unfortunately, the name is so long and complicated that it's scary. So a lot of people, when they learn dynamic programming, go, oh no, I'm learning this really complicated thing, and I don't even understand what the name means, so the whole thing's even more complicated. So I don't want to call it dynamic programming. I want to call it, what's a better name for it?
Recurrence programming.
Recurrence programming sounds better. Except recurrence is also a bit scary.
Super fun, happy time.
Super fun, happy time. Super fun, happy time. That's what we're doing. Okay, so we're going to learn super fun, happy time. What do we call it? Easy fun? Easy fun times. Easy fun times. So easy fun times works like this. Here's a problem. You're a king on a chessboard. You can move one piece in one square in any direction. You want to get to this square here. You're never going to backtrack. So you're always either going to be moving up or diagonally that way or across. You'll never go back down, because that would be dumb. How many different ways are there that you can travel from here to here?
A lot.
A lot is the correct answer. Well done. That was easy and fun. How many different ways? Does anyone want to know? Does it look hard to work out? It looks like maths. It looks like we're going to have to do some work and some thinking, and that's not an easy fun time. Easy fun time is when you don't have to do any work or any thinking. So what we're going to do is we're going to do this. We're going to solve the problem by relating it to easier problems. So we'll say, oh, I don't know, how many ways of getting to there if we start there? One. Oh, and none. We're already there. None. We're already there. There's nothing. Okay. What if we're here? How many ways of getting there? There's one.
I'm pretty sure there's one way from the start. You really want that to be one.
I don't know. We'll see.
Okay.
We'll see. I mean, I could have blown the whole thing up, but it's easy fun times. In easy fun times, you just go back and change it, and everyone forgets you made a big mistake. Okay. So how many ways from here?
One.
How many ways from here? Three. How did you know there were three? Shh. Because this is the clever bit.
Because they've got the one from up there,
You could go there,
or you can go to those other two.
or you could go here. Now, if you went here, how many ways are there from there? One. And if you went here, how many ways are there from there? So it's 1 plus 1 plus 1 is 3. From here, how many ways? Well, from here, how many ways are there of getting there? You can only go here, and from there, there's only one way of getting there, so there's only one. From here, how many ways are there of getting there? 5. That's correct. Because you could go here, in which case there's one way, or you could go here, in which case there's one way, or you could go here, in which case there's one way. Okay. How many ways from here? 1. How many ways from here? 5. How many ways from here? No, you can work it out. 13. Because you could go here, there's 5 ways from there. Here, there's 5 ways from there. And here, there's 3 ways from there. How many ways from here? 1. How many ways from here? 6. How many ways from here? 7. 5 plus 1 plus 1 is 7. That was fun. I like making mistakes. What's this? 25. 1, 7, 25, 63. Oh, that's interesting. So, there are 63 ways. How hard was that? Let's be honest. Was that at all hard? You just had to know how to do it. You just had to remember how to do it, didn't you? And if you remembered how to do it, it was very easy to do. What made this problem so easy to solve, and what we've just done, by the way, is called dynamic programming. What made this problem so easy to solve was when you were solving this guy here, you already by then had filled in the solutions for smaller examples of the problem. Yep. You already knew the solutions for smaller examples. And furthermore, to solve the bigger problem, all you had to use, and it was quite valid to use, was the solutions to the smaller problem. So if we wanted to make the problem even crazier, if you wanted to do something like, okay, we're going from here to here, but you're not allowed to pass through this square. Now maybe you could have come up with a formula to work this one out, but this is now a bit harder to work out. But again, we can just work it out in the same way. 1, 1, 1, 3, 1, 1, 2, 1, 5, 8, 10. There's 10 ways. Because again, once you get to say here, there's 3 ways of getting there, and it doesn't matter whether you got there from here or from here. It doesn't matter how you got there, the history is irrelevant. The optimal solution from here is also the optimal solution from anyone that passes through there. This is called optimal substructure, which again is a fancy name for it. Optimal substructure means that to solve the big problem, you have to solve smaller problems, and the optimal solution for the big problem uses the optimal solutions for the small problem. Now, if the optimal solution for the big problem didn't use optimal solutions for the small problem, then we couldn't do what we've just done here. It wouldn't work. Yes?
Would this have been effective for something like BCB, where you say, calculate all the 5 ones, you just save all the 4 length program states and use them to calculate the 5 ones? And you save all the 5 ones to calculate
That's a really good question. No, because I think that breaks optimal substructure, which is the 5 one that does the most work is not necessarily a component of the 4 one that, of the 6 one that does the most work. Yeah. Or another way of looking at it is the shortest. Suppose I have to travel from. Yes.
So every program of length 5.
Yes.
Yeah. Will step 1 and become a program of length 4.
No.
No.
No, because the 5th instruction is still there.
Yeah. Oh. No, sorry, not length 5, but runs 5 steps.
Yes.
Yeah.
But it's got a different state to the initial state. It could possibly have changed state.
Okay, yeah.
Yeah. So all your initial programs of size 4 start with all registers set to 0. But when you turn into a program of run 4. Oh yeah, you maybe could. Yeah. You just got to pick your states. You've got to design the subproblems in such a way that they exhibit optional substructure. Now there's many ways of carving a problem up and saying what the subproblems are. That's right. But just if you've got a program which takes 7 bytes, and now you want to work out something about programs which take 8 bytes, unfortunately you can't just remember the best 7-byte programs and use them to work out the best 8-byte programs, because it may well be.
But could you example save all the 7-byte ones and the result of those 7-byte ones, for example, the registers end up, R0 ends up with this, R1 ends up with this, and therefore you just got to do the last command. So you don't have to calculate the first 7 programs again.
It is certainly the case that in the Busy Beaver problem, you can use Memoization, which is what we talked about before. Memoization is when you have to calculate something, instead of calculating it every time, you notice you've calculated it before and you just remember what the answer was. So certainly in the Busy Beaver problem, there was much scope for thinking, oh, I've been here before, and it took 100 steps from here. Yeah, absolutely do that. That's Memoization. But that's not, dynamic programming involves memoization, but it involves more. So memoization is, every time you do something, you record what you've done. And the next time someone asks you to do that same thing, instead of doing it, you just give them then the answer, you record it. It's like a top-down way of remembering stuff. So as your program goes, it does function calls, and every time there's a function call, you remember the result of that function call, and if you ever have to do that function call again, you know the answer. And you don't have to work out values for function calls you never make. It only works out on the fly as you need them, on demand. It creates them, exactly like we did for the Fibonacci thing. That's memoization. It's a great technique. Dynamic programming, though, what we're doing now, you'll see, is slightly different. In a sec, you'll see it's slightly different. Let's talk a bit more about memoization, just so you get really grounded what memoization is. Suppose you're sitting your driver's license test, and there's some multiple choice questions you've got to fill in. And they've got a bank of 100 multiple choice questions, and they pick 20 of them at random, and you've got to, do you have to get them all right? You don't have to get them all right. That's insane. You've got to get 36 right, you can get 4 wrong. And if you ever get a ticket for one of those 4 things, are you allowed to then get out of it saying, no, that's all right? I got a certification here saying I didn't need to know that. All right, so you've got a bank of 100 questions, say, and suppose you have to get 20 of them, you get given 20 of them. How many different ways are there, you're studying for the test, how many different exams are there that you could generate? 100 C20, which is huge, right? The number of ways of picking 20 objects out of 100 is vast, very, very large. You couldn't practice every possible exam there is. So can you see from the point of view of the problem, there are many, many things to be done. So if you are a forgetful person and never bother remembering anything, like in Fibonacci, and every time you see something you go, whoa, that's new, and you have to work it out again, the number of exams you would have to go through to cover all the exams, if you wanted to search and find a perfect exam or something, you would have to do 100 C20 of them. But there is the state space of the problem, can you see, is much, much smaller than that. Essentially, there's only 100 questions they can ask. So if every time someone asks you a question, rather than working out the answer and scratching your head and trying to remember what the answer was, or trying to work it out, you just remember every time you answer a question what the answer was. Suppose it takes you 20 seconds to work out the answer to a question normally, but if you've memorized it, it's on your chart, you can find it in 1 second. Well, no, suppose it takes you 5 minutes to answer a question normally. Yeah. And if it's on your chart, you can do it in 1 second. Then you can see that the first few exams you'll do quite slowly, but as you start memoizing the results for each question, towards the end, you'll start doing things much, 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 much faster. Can everyone see that? And towards the end, all your exams will only take 20 seconds to do. That'll be awesome. So memoization has given us a big speed increase. But notice what it hasn't done. It hasn't changed the complexity of the problem. If we have to go through every exam to look for something, this is just letting us answer the exams faster. But we still have to go through the same number of exams. So it hasn't changed the complexity of the problem, but we're remembering stuff, it's speeding us up, but we're not remembering stuff and changing the complexity. However, sometimes when you do this strategy of remembering what's happened before and not doing it again, you can change the complexity of the problem. And that happened for the Fibonacci problem. We broke it into 2 sub-problems. I'm going to ask the question I asked you at the beginning of the first lecture. When is it worth remembering stuff? It's worth remembering stuff if you're going to have to do it lots and lots of times. That's memoization, because that is going to speed you up. It's superly worth remembering stuff. Why was Fibonacci different? Why was it that memoizing remembering 41 and remembering 40, if we're working out Fibonacci 42, why is it that remembering those actually change the complexity of the problem? Because you see with the exam one, before we had 20 questions, each would have taken 5 minutes. How long would it have taken us to do? 100 minutes. After the speed up of the memoization, each exam takes us 20 seconds. So that's a 300 times speed up. And we all know a 300 times speed up, is that a 300? Did I get that wrong? Yeah. What is it, 30 times? It's either 300 or 30 or something like that. How many 20 seconds in 100 minutes? 300. 300. It's a 300 times speed up. Okay. Going. Okay, I've been thrown now. So that gives us a 300 times speed up, but a 300 times speed up doesn't change complexity. But here, we're not getting a 300 times speed up. We're changing from something that's exponential. How many calculations do we have to do to calculate Fibonacci of 42? Approximately. Once we memorize them. We have to do approximately 41 calculations. It's order n. So we've gone from an exponential algorithm to a linear algorithm. How did memoization speed that up? This is the million-dollar question. What properties did the problem have that meant remembering the answers gave us a huge payback? Because this is one time where it's absolutely worth remembering stuff. Even though it's a space-time trade-off, now we've got to remember use a bit of extra space to remember stuff. But the time payback is so big, we love it, because it gives us a complexity change. What is it? What is it about this that not having to work this out is really cool? Why is it not having to work this out different to not having to work out an answer in an exam?
If you work that one out, it eliminates everything else.
Yes. Yes. Because this is not just something that takes a constant amount of time to solve the naive way. In the exam, to solve the questions a naive way takes a constant amount of time, which is 5 minutes. In this problem here, to solve the subproblems, the cost of solving this is not constant. What's the cost of solving f of 41? It's exponential. Memory gives us a constant time lookup. If we're replacing a big constant number with a small constant number, woohoo! But if we're replacing an exponential thing with a constant thing, whoa! So absolutely, so the thing about here that gave us a clue that it was going to do this was it was the same problem. Solving this was just a larger instance of solving that. So this has presumably the same complexity as that. Yeah. So we do dynamic programming. We love dynamic programming when we have some problems which are, if we did them the naive way, they would not be linear to solve. And in fact, we do dynamic programming when the subproblems, if we did them the naive way, the subproblems are in fact the same as the original problem. And the original problem, if we do it the naive way, is not linear, so that's why we need to apply dynamic programming to it. So what we like, memoization can be useful for things other than dynamic programming, but the particular case that's dynamic programming pops up all the time, we really like it, and that's when a problem is defined in terms of subproblems. So it looks a bit like divide and conquer, but it's not divide and conquer. This is actually what we call chip and conquer. Divide and conquer is when you get a big problem and you break it into 2 half problems that are roughly equal size, or 3 that are a third size, or 4 that are a quarter size, and you get that complexity payback just from splitting them up. Here, we're getting the complexity payback by splitting it into subproblems that are essentially the same as the original problem, and noticing that in the expansion tree for these subproblems, certain subproblems are going to appear multiple times. So we have multiple instances of the subproblems popping up, or what Bellman called it was overlapping subproblems. So the subproblems you're generating, if you didn't cut it off here, you would generate the same thing over and over a bazillion times. So memorizing the result not only means we can look it up instantly, but means we never have to go down here and generate the problem a bazillion times. In Fibonacci, you saw we generated 500 million objects to solve Fibonacci of 42. Now, we could have sped up the accessing of those objects, but if you're generating 500 million of them, you're still looking at 500 million sub-problems. That's going to cost you 500 million work Maybe it's 2 times 500 million, maybe it's 8 times 500 million, maybe it's 1,000 times 500 million, but it's still 500 million work. It's still exponential in the case of the Fibonacci. But here, if we memoize this, it means we don't do that work. We don't generate those extra objects, so it's made a linear, just a linear lookup. Yeah. So we do dynamic programming is, we've got a big problem, we break it into a slightly smaller sub-instance, or maybe 2 smaller sub-instances, or 3, or whatever. You saw Fibonacci split 2 ways. This one here, how many sub-problems do we break it into? To work out this guy, how many sub-problems did I need to solve? 3. I needed to know the best solution for here, the best solution for here, and the best solution for here. Each of these problems is only slightly smaller than this problem. And the problem is, in solving this one, I'm going to have to solve this one again. And in solving this one, I have to solve that one. So already I have to solve this problem twice. So when you've got overlapping subproblems, you save their results, and then you never bother generating the overlapping subproblems, you just generate them once. Does that make sense? So we want the optimal substructure, which is we want the optimal solutions to the subproblems to actually be part of the optimal solution to the big problem, so we can reuse them. But that's not going to give us any payback by itself. The big payback comes as if we solve the same little problems over and over again, then using this strategy of dynamic programming, we make sure we solve each little problem only once. I wanted to, where we got to this when we were getting to questions, just when you asked your question, I was just about to talk about optimal substructure and what it means, because it's such a fancy sounding phrase. And the example I was going to give was this. Yeah, okay, here. The fastest flight from here to New York, say. Oh, and you're on some crazy world where you have to take lots of legs on the journey. Maybe fastest boat trip from here to New York. Now, if you worked out the fastest boat trip from Johannesburg to New York, and you knew how long that took, then if I work out the fastest boat trip from here to Johannesburg, then I can use that information combined with this one to give me the fastest journey from here to New York via Johannesburg. Yep, that's optimal substructure. But what if it's the case that the fastest way from getting from here to Johannesburg is through, and here my geography is not very good, is through North Korea. And I can get there really fast through North Korea. I want to go from Sydney to Paris. That sounds even better. Woohoo! Now I can see the Eiffel Tower. I want to go from Sydney to Paris. Maybe the fastest, and there's Johannesburg. And there's New York. Now maybe the fastest flight to Paris from Johannesburg passes through New York. Fastest boat trip. Maybe it does, I don't know. And maybe the fastest trip from Sydney to Johannesburg passes through North Korea. What's it? Pyongyang, how do I say it? Pyongyang? How do I say it? Pyongyang? P1. Oh, I just wrote P1. Yeah, okay. Sorry, I'm just terrible at pronouncing things. Maybe the fastest way of getting from here to here is via here, and maybe the fastest way of getting from here to here is here, but that does not mean that the fastest way of getting from here to here via here will be the composition of these two, because once you've got that stamped in your passport, you wait forever when you come through here. Is what I'm trying to say. So it's not the case that you can consider these two things independently. It's not the case that once you're here, it doesn't matter how you got here, you now just have to work out the fastest way between here and that's the rest of the answer. Because how you got here actually counts in this problem. Or some other problems have constraints like this, like, you must be able to think of lots of scheduling problems. You're scheduling things, and maybe once you've put, what's something that really stinks, you can never get rid of that smell again? Exam. Bromide. My kids love bromide. I can't stand the smell of bromide. Maybe you've got some factory and you've got to schedule your mixing equipment to do things in various orders, but you can't work out the optimal way of doing things with the vats in a certain way to get to a certain state. Maybe you've got day one and day two. It's not necessarily that if you find the optimum thing you can do on day one and you find the optimum thing from that spot to there on day two, It's not necessarily that putting those together gives you the optimum thing passing through, because it may well be that on day 2 you need to use the big vat to mix the chocolate, and if on day 1 you use the big vat to mix the bromide, it'll still stink of bromide and it'll ruin the chocolate. Does that make sense? So if earlier decisions you make can affect future decisions, if the problem's structured in such a way that when you break it into the sub-problems, solutions to sub-problems depend on other parts of things you've already done, then it doesn't have this thing which we call optimum substructure. It's got to be that in solving the problem, once you get to here, no matter how you got here, you use the optimal thing from here to here. Or you use the answer from here to here. There are 3 ways. See, if I said here, you're not allowed to go through this path if you've ever visited this square, then this wouldn't actually work anymore. The numbers wouldn't work anymore because one of the journeys goes here, here, up here. And from here, we're not allowed to go to there in that time. Does that make sense? So there's one path not counted. Yep. I'm saying it over and over again. Oh, and we're at 6 o'clock. All right. Oh, let me give you a puzzle to take home. You've got a block of chocolate. Now, there's an easy answer to this, but I want you to work it out with dynamic programming. You've got a block of chocolate. I suggest you actually do this practice for real. You know when to melt chocolate, you've got to break it into little 1-by-1 pieces?
Well, thereabouts.
Thereabouts. And I've often wondered, what's the best strategy for breaking it into 1-to-1 pieces? Like, should you break them longwise into long, thin ones, and then lots of little thin ones? So, how many snaps? What's the strategy to give you the minimum number of snaps in a block of chocolate to break it into 1-by-1 pieces? The block of chocolate's n by m, as all good blocks are. Okay, what's your optimal strategy? What's the minimum number of snaps you can do, and what's the sequence you should follow? Now, you might work it out mathematically, and there are easy answers to work out mathematically, but I actually want you to work out how to do it with dynamic programming. When we meet on Thursday, I'll show you one more dynamic programming example, and we'll actually code it up. Okay. Come down the front if you've got questions, otherwise I'll see you on Thursday.